Another way to represent a nonlinear relationship in a regression is to use a quadratic term. So here we have our simple beta 1 times x1. This is just the linear term. But in addition to this, if we don't believe that x1 and y are related linearly, we might add this second term, which is the exact same explanatory variable x1, but this time we're squaring it. So we create a new coefficient for that new term, even though it's the same variable, just squared. Now let's take the exact same data that we looked at earlier that related test scores to median incomes. And remember, we decided this was not linear. It had this curve here. And let's say that instead of using logs, we decide that it's best to model this using a quadratic. So we look at a population regression function that includes both a term for income as well as one for income squared. And we run the data through this regression function, and we estimate these betas at 2.87 for income and negative 0.016 for income squared. If we plug in some values for income into our sample regression function that we estimated, so 10 and 11, 20 and 21, 40 and 41, we calculate the test score associated with each of these levels of income. And we calculate the change, which is just the difference in these test scores, the change in test score associated with raising income from 10 to 11, which is 2.5, from 20 to 21, which is 2.2, and 40 to 41, which is 1.6. We see that these changes are decreasing as we raise the level of income, which is the characteristic we want given the data that we have. So how do we actually interpret the values of these coefficients, 2.87 and negative 0.016? So the bad news is that we can't actually directly interpret the magnitude of these coefficients like we did for the different regressions using logs. We can only plug in our values for income and look at the changes in test score for various levels of income that we might care about.